Hello and welcome to the flipped recording for 1.11 Mechanical Energy Conservation. As we get started, don't forget that you do need to fill in your science notebook slide that will be submitted as your Part 2 test. So you need to complete each slide for each lesson as you work through the unit. If you wait till the end, it will take you so much time to complete. Remember, notes are required on those science notebook slides. They do help you learn the vocabulary, put down formulas and examples, just making sure to help you get the content that you are able to use on quizzes and tests. So I'll also be covering the guiding questions so that you can jot down those answers as we go. So as we jump into the lesson, let's take a look. As you log in, make sure you're going to the lessons under content, scrolling down, making sure that as you work in Unit 1, that every lesson has a check mark next to it, all the way up to where you're working, that you're not leaving anything there as numbers. And then we will jump right into the introduction. So again, this is where the guiding questions come from. They'll be on the next slide. So mechanical energy conservation. If you release a marble at the top edge of a bowl, will it keep going and rolling back up to the opposite side? Will it roll all the way out of the bowl? Most likely not. It doesn't have enough energy. It starts with potential energy, and that converts to kinetic energy, then back to potential energy. But the total amount of energy remains the same. And this is called mechanical energy conservation. So that's probably a good definition to go ahead and put in your notes. As we move on, you've got that mechanical energy word to go ahead and define. Remember, you want the words defined in your science notebook, not just listed. And then here are the guiding questions. I'll go ahead and take a little screenshot of those. Put them over to the side so that we make sure we get all of those answered as we're going. All right, so as we jump into the lesson, exploring this mechanical energy conservation, the first question, the guiding question number 1 says, what is mechanical energy? So you can see we have a lot of things going on here. When you drop a ball, it speeds up as it falls because the ball's gravitational potential energy is being converted into kinetic energy. But something is staying the same, and that is called mechanical energy. Mechanical energy is the combination of an object's kinetic and potential energy. And in a case like a ball falling from your hand to the ground, the mechanical energy stays the same. This is called the conservation of mechanical energy. So here's another definition that you probably want in your notes. You could take a screenshot of that, paste it over if you want it. But it's the sum of the kinetic and potential energies of an object remain at a constant value unless there are forces acting on the object that cause a loss of overall energy overall. That kind of sounds like Newton's first law, if you remember. And then watch the pendulum. So we're going to watch that in this video over here a few times. It says think about what the bars on the right are showing you. Okay, so if we look over here, we're going to be watching potential and kinetic energy as the pendulum swings. And if you're taking a look and you remember from the last lesson, we saw that as an object gains height, the potential energy is high, and then when it is got a very low height, the kinetic energy is high. So you're watching just those numbers go back and forth pretty consistently as the pendulum swings. So that was, we answered guiding question 1. Guiding question 2 says, describe a pendulum's mechanical energy. All right, so let's take a look. As the pendulum swings back and forth, 2 things change: its speed and height. The pendulum's speed determines its kinetic energy, and its height determines the potential energy. in this image, the pendulum is at the top of its swing where it has reached the highest or its greatest height. For a split second, it stops moving. And it has to do that because it has to change direction. So if you think about it, if you were swinging on a swing, the same thing would happen. Once you get all the way back, you have to kind of pause for a split second before you can move forward. So notice that in this moment, the PE bar is full, it's at its highest height, and kinetic energy bar is empty. So if we were describing that motion, that mechanical energy for guiding question number 2, we know that as it swings, 2 things change, its speed and height. And those 2 things affect the kinetic and potential energy. So that's how you would answer number 2. And then question 3 says, when is mechanical energy conserved and when is it not? All right, so we're looking a little more. So in this image, the pendulum's at the bottom of the swing, right? So it started up here and now it's reached the bottom, so it's at its lowest point. So if we look over here, we have no potential energy, but we have very high kinetic energy. So now the KE bar is full and the PE bar is empty. So this shows that all the potential energy has been converted to kinetic energy. Another way of looking at it is to see that the total amount of energy has remained the same. At first, it was all PE, now it's all KE. But the mechanical energy, remember that addition of both of those together, it remains constant. So the total energy remains the same. And in this image, you see that the pendulum is in transition. So it's between the highest and lowest points. And this means that it has speed, but not as much speed as it does at the bottom of the swing. So you can see that these are not one high and one all the way low. So it also has height, but not as much height as the highest point. So if you look at the bars on the right, there is some PE and some KE. But if you look carefully, you could pick up the piece of the PE bar that's filled and move it over to the KE bar and it would fill it up exactly. So it just shows that that amount of energy is constant. There is a set amount of energy in this movement of the pendulum, and that's its mechanical energy. Because remember, we defined that as the sum of kinetic and potential energy. So how much energy is in the form of PE and how much is in the form of KE just depends on where it is in the swing. So the total amount remains constant. So mechanical energy in action. Watch this animation to see the concepts of mechanical energy and the conservation of mechanical energy in action. All right, so we're seeing very similar. It's doing the same thing we saw on the last video or on the last screen. So if we're being asked to explain what we see, you can answer these questions to apply the concepts of mechanical and conservation. So at this point, so he's in the very middle, right? He's at the lowest point. What's true about the energy? So our answer would be, if we take a look, full KE, 0 PE. So it is all kinetic energy here. And if we look at that, KE bar is full, PE bar is empty. The total energy is all in the form of kinetic right now. So up here we can see that all of the potential energy bar is full. So if we look here, it's all potential. All right, so right here we can see he's not quite to the top, but he's gaining height. The PE is a little bit higher than the KE. So it's not all or nothing. It's almost half and half here. Okay, but if you added those up, if we had a number, you could fill one side with the other. All right, so moving on from there, is mechanical energy always conserved? And so this is where you'll find the answer for guiding question 3. You probably know the answer to this question. if you think of the skateboarder in a real life situation, would you expect him to be able to keep getting back up to the same height without doing any pumping? No. You would know that there's friction in the real world, which slows things down, and friction also uses up some of that energy. So imagine this boy on the slide. As he goes down, his PE is turning into KE, but he is also feeling the effects of friction slowing him down. Friction, we know, it's a force, and it's acting for a distance. So what does this cause? A force that's acting for a distance causes work. And in this case, the force is in the opposite direction of the distance the child is moving. So this means that it's negative work, which means the child is losing energy. So the friction is basically going up while he's going down. So if you drew bars to demonstrate the PE of the child at the top of the slide and the KE of the child at the end of the slide, they would not be equal because some of that energy was lost to friction. So when you're answering that question for mechanical energy conserved, it's conserved when there are no other forces acting on the scenario. And when it is not, when something like friction is introduced. So if we look at this paragraph, we'll see that in more detail. So in a pendulum, mechanical energy is nearly completely conserved, but a skydiver with his parachute open experiences a very different situation. The pendulum doesn't experience very much friction or air resistance, so there are minimal forces doing work causing the pendulum to lose energy. However, the skydiver's parachute comes in contact with significant air resistance. Likewise, the child on the slide feels significant friction. These forces do negative work on the object and cause it to lose energy. So when is mechanical energy conserved? It's conserved as long as there are no significant friction or air resistance affecting the object. So that is the exact answer you need to fill in for guiding question 3. So how much energy is lost to friction? The energy lost is the difference between the initial mechanical energy and the final mechanical energy. All right, so we're moving on. We've answered all the guiding questions. Take a look. This is just a simulation showing you changes in energy as a way to observe those. So it says, drag the rubber ball from the toolbar and set it on top of the ramp. Let it go and observe its motion. Consider how its energy changes as it travels down the ramp. So we've got a ball, putting it on the ramp. Potential energy would be high here because it's at its highest point. Okay, so we're seeing what happens. Before you release the ball at the top, we know it has potential energy. When the ball, how does the energy of the ball change as it rolls down? We know that the potential energy goes down, but it's converted to kinetic as it reaches this area and stops to change direction. And does the ball return to the same height after it bounces each time? No, it does not. And is mechanical energy conserved in this simulation? None. So no mechanical energy is conserved in the simulation because the ball eventually stops moving. So we can see that movement getting smaller, smaller, smaller. So forces like friction do negative work on the ball and cause it to slow down. So we can see that right now it's not moving because enough friction has caused the negative work and it has stopped. All right, so how much energy is lost? Consider the case of the child on the slide. If the child has a mass of 30 kilograms and is 5 meters off the ground at the top of the slide, what kind of energy does he have and how much? So this looks just like what we plugged in last lesson. We have his weight, 30 kilograms. If we were trying to solve the potential energy, we could just plug in that 9.8, and then the we don't have a height though, so we can't get. Do we get a height? Oh, 5 meters. 5 meters off the ground. So So yes, we can plug in all those numbers, 30 times 9.8 times 5, and that gives us 1,470 joules. So now he's sliding down. So we have some movement. If the mechanical energy was conserved, what would happen? So now all of that potential energy would turn into kinetic. So if the mechanical energy was conserved, which it was in our example of the Ferris wheel a while ago, there would be just as much KE at the end as there was PE at the beginning. But the child's speed when he comes to the bottom of the slide is 5 meters per second. So how much kinetic energy does he have? So we take 1/2 of the mass times the velocity squared. So 1/2 of 30, so it's going to end up being 15 times 25. We have an answer of 375. So the PE at the beginning is bigger than the KE at the end. Where did that missing energy go? If the work was done by force of friction, if work was done by the force of friction, how much work was done? So we take those two numbers and we have to subtract. So the difference there from 1,470 from potential to kinetic gives us 1,095 joules to show how much work was done by friction. All right, so here's a great fill in the blank. I suggest practicing with these words, checking to make sure you get it right, then take a screenshot and put this in your notes. And then here is your notebook activity for this lesson. It says in your science notebook, construct an argument to support the claim that when the kinetic energy of an object changes, energy is transferred to or from the object. So use evidence from the simulation in the lesson and your own experiences to support your claim. For example, how does the kinetic energy of a basketball change after you drop it? So some of the kinetic energy is transferred as sound when the ball hits the ground. So basically it's asking you to explain a scenario like this. So basketball bouncing, someone on a slide, someone on a swing. Maybe you can think of another example. I think that drawing it out allows you to pinpoint areas of high and low or equal potential and kinetic energy, which might make it a little easier to explain in your own words. So don't forget to do that part and put it in your science notebook. So with that, we've reached the end of the lesson. Taking a look at the lesson review, make sure you can answer these things. When back and forth motion is observed, such as a skateboarder on the half pipe, energy changes from kinetic to potential energy and back again. In situations like this, the total energy is conserved. So answer the following questions. Just make sure you know these. They look very similar to those guiding questions that we answered as well. So from there, we are finished for the day, so we'll see you on the flip side. Look for the flip follow-up sessions in your class, and come see me in Help Lab if you need any extra help. Have a great day.